2. This is section 2.7. We talked at the very beginning of this chapter about changes of state, going from a liquid to a solid or a solid to a liquid, all different variations of that, and that was a physical change, not a chemical change. And so what we're going to do is, because this is the energy chapter, we show you how changes in state can either absorb or release energy. And the example that I give you here first is that if you take a gram of steam and the steam condenses, you will release 2,260 joules. A substance is said to be melting when it changes from a solid to a liquid. It's freezing when it changes from a liquid to a solid. So water has a freezing melting point, depending on which way it's going, of 0 degrees Celsius. So a solid requires heat to change to a liquid from a solid, or a liquid gives off heat if it changes from the liquid to the solid. So let me say that again, make sure I said it right. A solid requires heat to change to a liquid. A liquid releases heat to change to a solid. The heat of fusion is the amount of heat you release when 1 gram of liquid freezes, that is, goes to a solid at its freezing point. It's the amount of heat needed to melt a gram of solid at its melting point. So these are the same points. So for water, that's 0 degrees. It's either, if it's cooling, it's freezing. If it's heating up, it's melting. Okay, so see why those are really the same thing. If a solid goes directly to a gas, that is called sublimation. If a gas goes to a solid, it's called deposition. Okay? The heat of fusion for water is 80 calories per gram, or 334 joules per gram, depending on which system you're going to use when you're doing the calculation. So, if you're going to do calculations with heat of fusion, just like we saw with specific heat, you've got grams of the substance and what change of state you're doing. You're going to have to convert grams to heat by using those conversion factors. And basically you just set that problem up. So our first question is, how many kilojoules are released when 25 grams of water freezes at 0 degrees Celsius? Okay, so go back, look and see what our definitions of those were, see what kind of conversion factors I gave you, and see if you can work this problem without looking at the answers. So you have 25 grams of water, okay, and we're going to freeze that, which means we're going to turn it into a solid. So how many kilojoules is that going to take? So we're going to go from grams of liquid water to kilojoules. So we know that the conversion factor is either 334 joules per gram of water or 1 gram of water to 334 joules. And we also know kilojoules and joules. There are 1,000 joules in 1 kilojoule. So we've got those conversion factors that we may need. So then what we do is, we know we've started with 25 grams of water. We know that the next thing you put to cancel is going to have to be grams of water on the bottom. So our conversion factor, which was 334 joules per gram of water, so we can cancel those. We're left with joules, but we want kilojoules. So we just put joules down here and put our conversion from joules to kilojoules, and that gives us 8.35 kilojoules. So if you start with what you're given, you know, if you're going to use dimensional analysis, that the next thing is going to be grams of water, just like you had here, and the conversion factor, so that leaves joules on top, and then you convert joules to kilojoules. Okay, very simple. Easy for me to say, right? How many joules are needed to melt 15 grams of ice at 0 degrees C? Start with your 15 grams. You're going to use, since you're looking for joules, you're going to use your joules per gram of water and do your calculation. So here's your setup. And you've got 15 grams of ice, because it's a solid, times, you know, grams of ice is going down here, so 334 joules on top, and so 15 times 334 gives you 5,010 joules. Water evaporates if the molecules on the surface have enough energy to turn into a gas. It condenses when the gas molecules lose energy and form the liquid again. Okay, so in evaporation, that this reaction here is occurring, this change of state is occurring on the surface of the liquid. Okay, so the gas is converting back to liquid, the liquid's converting to gas, and so that's happening right there at the surface of the liquid. When it boils, all the water molecules get enough energy to form a gas. The bubbles of the water vapor are going to be all throughout that because it's converting to the gas from the bottom all the way to the top. And so as they do that, they're going from, you know, all throughout it. It's not just occurring like evaporation at the top. It's all throughout the water. Heat of vaporization, as in like evaporization, is the amount of heat that you absorb to change a gram of liquid to gas at the boiling point, or how much you release when 1 gram of gas changes to liquid at the boiling point. Okay, so vaporization is where liquid goes to gas. Condensation is where the gas goes to the liquid, and they're reversible. And if you like put a lid on a boiling pot on the stove and you lift that lid up, you'll see the water that's been condensing on the underside of that top, and that's where it's condensing. It's vaporizing, it's getting trapped on that top, and it condenses back because the top is cooler than the boiling water. We know the boiling point of water is 100 degrees C, and so that's where this is going to occur, at 100 degrees. So the heat of vaporization of water is either 540 calories per gram or 2260 calories per gram of water. Okay? So here we go. We're going to set this up and do using heat of vaporization. How many kilocalories are released when 50 grams of steam from a volcano condenses at 100 degrees C? You've got kilojoules. You start with grams. It's going to be very similar to the other problems that you worked. You're just going to be using heat of vaporization. All right, so you got 50 grams of water. You're going to go from grams of water to kilojoules because you're condensing. So you've got 2260 joules per gram of water, and 1 gram of water over 2260, same thing. If we've got to go kilojoules to joules, we know that's a factor of 1,000. We start with the 50 grams. We use our heat of vaporization or condensation to get rid of grams of water, which leaves us with the joules on top. Then all we do is convert our joules to kilojoules, cancel those, and the answer is 113 kilojoules. Sublimation, very cool by the way. Dry ice. This is where the solid goes directly to a gas. So you see this solid, it's nitrogen, okay? Or it can be other things, but solid nitrogen, and it will sublime. And so that means that as you see that gas coming off, okay, it is coming off as a gas. And so it doesn't go from a solid to a liquid to a gas. It goes directly from the solid to the gas. Dry sublimes at about a negative 78 degrees C. It takes place in frost-free refrigerators. You also can buy it, and you can prepare freeze-dried foods and things like that. So this is called the heat of sublimation. You see the pattern here? They're very, very similar, okay? 620 calories per gram, or I think that should be 2590 joules per gram for your sublimation. Okay, and so again you have this sublimation, and I love my little snowman picture here because it really kind of brings it you know, kind of into focus for me, because you know I like pictures. So we have a snowman that's a solid. If he sublimes, he goes directly to a gas. If the gas deposits back, it forms the solid. If our solid snowman goes to a liquid, he melts. If the liquid freezes to the solid, it freezes. The gas condenses to a liquid. The liquid vaporizes to a gas. So you see how this kind of is a circular thing? And so you can kind of think about it in this way and just remember what those terms are. In science, in chemistry, physics, engineering, we use something called a heating curve in order to show what's going on with these changes in states. And if it's going up, like the temperature is increasing, we call it a heating curve. If the temperature is decreasing, we call it a cooling curve. So on a heating curve, what you see that the diagonal lines, okay, are where we are all one state. Okay, so in this diagonal line here, we're a liquid. When you get a horizontal line, that's where you're changing state. So if you have a solid, when you reach your melting point, it's all solid until you get to this temperature, which is the melting point. Once it gets to the melting point, it stays at that temperature until it all melts, and then it will absorb heat again, okay, until it gets to its boiling point. And then it will stay at its boiling point as it converts from a liquid to gas until it is all gas, and then it will continue to rise in temperature. And just basically the opposite is true for the cooling curve. You add heat to increase temperature, you remove heat as you decrease temperature. So, learning check. A plateau or horizontal line on a heating curve represents what? A sloped line on a heating curve represents what? Right. Flat line is a constant temperature while it changes state. The slope line, the temperature is changing, and the state is not changing. It's the same exact thing. So here's the cooling curve. Like I said, the opposite. Again, you are decreasing in temperature in the slope lines. The horizontal lines stay the same temperature, but you're changing state. Okay, so it's just the opposite of the heating curve. All right, water condenses at a temperature of what? And you can look back on those heating curves to answer these. At a temperature of 0, liquid water does what? Freezes, melts, or changes to a gas. At 40 degrees C, water is in what state? And when water freezes, heat is what? Removed or added? Water condenses at 100 degrees, just like it vaporizes at 100 degrees, or boils at 100 degrees. At 0, liquid water will freeze. At 40, water is a liquid. And when water freezes, it gets cold because you've removed heat from it. That's why it gets colder. To reduce fever, you pack an infant in 250 grams of ice If the ice is at 0 and it melts, it warms to body temperature 37 degrees. How many calories are you removing from that body? What's the change in temperature? The change in temperature is 0 to 37 degrees if it goes all the way to the body temperature, right? So that's a 37 degree change. You've got 250 grams. You've got a delta T of 37 degrees. Okay. So if you've got 250 grams of ice, 80 calories per gram is 20,000 calories. The delta T is 37. So 250 grams times 37 degrees C. These should be like over here under this. 1 calorie over grams degrees C. So you can cancel all of that. That'd give you 9,250 calories. In this case, since you're changing two things, okay, then you have to add those two together. So you add the 20,000 and the 9,250, and if you use your correct sig figs, approximately 29,000 calories. When a volcano erupts, 175 grams of steam at 100 degrees is released. How many kilojoules are lost when the steam condenses and then freezes? Okay, so you've got two steps. It's going to first condense and then it's going to freeze. Okay, see if you can go back and look at all the information that we've done so far and come back and do this problem. You've got 175 grams. It's at 0. You're going to condense it at 100 degrees and then cool it to 0 and freeze it. So you're basically doing a cooling curve, right? You have steam, which you're going to condense at 100 degrees and change it to a solid at 0. Okay, so you've got several different parts of this cooling curve. You're going to have conversion factors. So this kind of takes everything that we've been doing in this chapter and puts it all together. You've got 334 joules per gram of water. Okay, that gets you liquid water to solid water. You've got 2260 joules per gram of water to go from a gas to a liquid. And the specific heat of water, which is 4.184 joules per gram degrees C. Now this is like the exciting climax of the whole thing we've been doing, tying it all together sort of. Alright, so the steam is going to condense. So you've got 175 grams, 2260 joules per gram times the conversion factor to kilojoules. That gives you 396 kilojoules. Water cools then from 100 degrees to 0. So you've got 175 grams times 100 degrees, because 100 minus 0 is 100, times what? The specific heat of water, and then the conversion factor of kilojoules to joules, which gives you 73.2 kilojoules. Then you have to freeze the water, which takes 334 joules per gram of your 175 grams, and then conversion, and that gives you 58.5 kilojoules. And so all three of those steps have to occur in order for this to happen, and so you have to add the energy required in each step, and the total gives you 528 kilojoules. Whew, that's a toughie. Well, the good news is that does it for Chapter 2. That's the end of Chapter 2.7. Thanks for staying with me. If that last one got you, go back and review it. But basically, you're just putting everything together that we've learned in the different sections of the chapter to work that one big problem of changing states.